With Section 2.5, we start our journey into the wonderful world of proofs. First, don't freak out. I know there are a lot of bullet points over there to the left. However, most of them should be review. You should already know most of them from your algebra days. Let's begin. First, we have the addition property of equality. You should have done this in your algebra class last year. Two quick notes before we start on it. First, the addition property of equality is the full formal name of the property. Most teachers won't worry about the of equality bit, and simply putting the addition property is sufficient. The full formal name isn't used a lot in practice. You will occasionally see it used that way in the book, and there are some teachers that will require it. If you want to use the full name, you can. It is more thorough. The second point is we aren't going to be asking you to memorize this property. We're never going to say, spit out this formal definition of the addition property. That just isn't how it is used in geometry. We just need to be able to identify when it is happening. That might not make sense now, but I will show you examples later about what we mean by that. So stay tuned. Now about that property. In algebra, you most often use the addition property kind of like this. 2x minus 8 equals 32. Next step to solving, for most people, would be to add 8 to both sides of the equation. That was the addition property. In geometry, that is what you need to be able to do. Identify that it was the addition property that was used to justify why you were allowed to add 8 to both sides of the equation. That's what you need to do instead of spitting out what the definition of the addition property is. There will be more examples later. That addition property allowed you to get to 2x equals 40. In algebra, that was by far the most common usage of it. However, if you look closely at the definition, there is a plus c on one side and a plus d on the other side. You are allowed to do that since c equals d, which in this case was 8 equals 8. But while it was most common in algebra to add something that was the same on both sides, in geometry it's going to be very common for us to be adding two things which look different, but it's allowed because they are equal. Here's an example. Let's say we know that AB equals CD, and we know that EF equals GH. With the addition property of equality, we can say that AB plus EF is equal to CD plus GH. That will be a very common thing to do. It looks a little different than when we simply added 8 to both sides of an equation, but we are allowed to do it since EF is equal to GH. Just be cognizant that it will be common to use the addition property that way in geometry. The subtraction property of equality should also look familiar. Like the addition property, this is the full name for the property, but most teachers will say that subtraction property is sufficient. Like the addition property, you'll often do something like this, where we subtract something from both sides of the equation that doesn't look the same, but we are allowed to do it because they are equal to each other. Overall, it works very similarly to the addition property. The multiplication property of equality lets you multiply both sides of an equation by the same thing. Same deal with the name too. This is the full formal name, and you don't have to write out its definition, only identify when it's being used. The division property of equality is just about the same as all the other ones so far, except they restrict it to say that you can't divide by 0, since dividing by 0 is always bad. You don't want to divide by 0 and be responsible for the ending of the universe as we explode, and then it gets sucked into a black hole, do you? Huh? Do you? I didn't think so. No dividing by 0. Ah, the good old reflexive property. This seems pretty dumb, right? Yay, A equals A. It's like the response when you have a postulate. Well, duh. However, I am sad to report that even though this looks pretty dumb, there will be a couple certain specific situations this year that you are required to use it. We will go over those times when we get to them in later chapters. One thing about the name here, though. Yes, this once again is the full formal name for the property, but there is one extra piece to this one. There is also this reflexive property. Here's where the name issue crops up a little more. In the top one, we are dealing with equal signs, and thus it is the property of equality. In the bottom one, we are dealing with congruent symbols, and there it is the property of congruence. They are both equally as dumb. They are both a reflexive property. Here's what you need to figure out if your teacher is going to want you to use the full formal name to identify which of the reflexive properties you are using. Many teachers will be like me and not worry about that a bit. For me, just saying reflexive property is good enough to cover both cases. They are fundamentally the same thing. Here's the only slightly less dumb property. Oh wait, that's not the right name. What is it again? Oh yeah, the symmetric property. I said the reflexive property comes up here and there and is required. The symmetric property comes up extremely rarely. It's the endangered species of the bunch. It rarely gets seen. Just like the reflexive property, the symmetric property has two flavors, one for equality and one for congruence. They are fundamentally the same thing, just one has equal signs and deals with numbers, and one has congruent symbols and deals with shapes. The transitive property I briefly did in the last section when I went over the law of syllogism, but it should also look familiar from your algebra days. Just like the last two properties, there is an equality version and a congruence version. Same deal applies with the name as the reflexive property and the symmetric property. Now we come to the substitution property of equality. On the face of it, this looks about as dumb as the reflexive and symmetric properties. That doesn't seem that interesting. In algebra class, they might have introduced the property to you doing something like this. And then you can use the substitution property to do this, which actually isn't that useful that often in algebra. However, we are going to be doing proofs here in a second. We will start off with algebraic proofs to get you used to the style of them, but when we transition over to geometric proofs, it is amazing how often the substitution property is used in a geometric proof. When we get to that point, I'll show you how it ends up being used. At this point, you probably have a hard time imagining how this property can be much use at all. Now to the distributive property. This is the first one where the full formal name doesn't include of equality or of congruence. This is the full formal name just as is. I won't say too much about this one. You probably did it once, twice, 4 million times in algebra class. And now we finally make it to proofs. Proofs are not popular. I are smart. I know this. Lucky me, I get to teach them every year. You know what? I know it's a joke, but it rankles me to see those misspelled. Let me fix that. Much better. Moving along. Proofs are a major test of your deductive reasoning and problem-solving skills. For 95% of you, proofs will not come up in real-world situations. However, honing those problem-solving skills are one of the most important things that you can do to be successful in life, so it is worthwhile. I have been teaching geometry for a while now. I know a lot of the ins and outs and tips and tricks that will help you out. If you follow all of the guidelines about proofs that I will give you over the year, then they won't be so bad. And some of you may actually like them. They might actually be fun. Some of you will embrace the problem-solving challenge they pose. Shocking but true. There are many different types of proofs. 2-column proofs, paragraph proofs, flow proofs, induction proofs, and so many more. We will give you a taste of a lot of different types of proofs this year. Are you excited? But most of the time we will be using 2-column proofs. So that is what I will show you here. This is the basic structure of a 2-column proof. I'm going to guess you can figure out where the name comes from. At the top you will see a line that says given. In a proof you are to always assume that whatever was given to you is true. Sometimes there will be one statement that is given to you. Sometimes there will be multiple statements. When we do a geometric proof, you will also often be given a picture like this. The given information is your starting point. The ending point is the prove line. The whole idea of a proof is to get from the given information to the prove statement. You need to find a logical path from one to the other. Sometimes that path may meander a bit as you search for a way how to get there. But in the end, the goal is to figure out how to make your way to the finish line. That's all you are doing in a proof. Starting from the given, make your way to the prove. Here's the first proof we will do. It is an algebraic proof to ease you into all of this. Since it is an algebraic proof, we don't have a picture to use, which simplifies things even more. You can see the information that is given that we are to assume is true. Our goal is to take that equation and get to x equals 3. Let's see how we go about it in proofland. First, there is good news when staring at a proof for the first time. There are free points available. In a proof, almost 98% of the time, the given information is going to be the first statement. So you can put it in for statement number 1. It doesn't absolutely have to be the first statement. The only requirement is that the given information shows up before it is used in your proof. So sometimes people will put the given information after statement number 1 if it isn't used until much later in the proof. That does make some sense. However, the good news for you is it is never wrong to put it first. You can always put the given information first and it will always be right. Those are free points. In a proof, as we make our way from the given to the prove, we will be taking steps. At every step along the way, we need to justify why we are allowed to take that step. That is why there is a reason column. With proofs, we want to use deductive reasoning. We want our conclusion to be definite. The only way that works is if we show that each step that we used along the way is justified by something we know is true. For this proof, we need to justify why we were allowed to put the given information in statement number 1. The reason you are allowed to do this was that the information was given. So you can always fill in those 2 boxes and they will always be correct, but we aren't done. The last statement of the proof is always going to be the prove line. That's your finish line. That's your end goal. It's always going to be the last thing. So you can fill that in too. Look at all those free points. The proof is half filled in and we haven't even considered how to do anything. You can do that automatically. But now our free points are done. Even though we can fill in the last statement, we don't know the reason for it yet. That will come based on how the proof progresses. You will see here soon enough. One quick note. On this proof, I have told you how many steps the proof will take. This is not normally the case. Usually it will be an indeterminate amount of steps needed. So in cases like this, you might start your proof out like this. You can put the statement number 1 and the reason number 1 in, but you don't know for sure how far down the last line will be. So you can put in the last statement with an unknown line number to start yourself out. This will be more common than the initial way I had laid out. Speaking of that way, Let's get back to it. We now need to consider how to make our way through this. If this was presented to you as an algebra problem, what is the first thing you would do with 4x plus 7 equals 19? For most people, they would subtract 7 from both sides. That's fine. Let's do that. But you won't see this anywhere. Even though that is what we want to do, that isn't what shows up in the proof. In the proof, we need the result of that operation. We take the result of that operation and put it in as statement number 2. Now we need to justify that step. We need to give a reason for why we could go from 4x plus 7 equals 19 to 4x equals 12. So what did we do? We subtracted 7 from both sides of an equation. So you need to ask yourself, what property, postulate, definition, theorem, or whatever allows you to subtract an equal quantity from both sides of an equation? It was the subtraction property of equality. I told you earlier that we wouldn't be asking you to spit out the definition of those things. That isn't how it is used in geometry. I told you you would be wanting to identify when it is happening. Well, here it is happening. Here we subtracted 7 from both sides. So that's when you need to put a name to that occurrence. You need to be able to say that's when the subtraction property of equality was used. Let's look at the next step. We already have the next statement as x equals 3. The question is why? Why are you allowed to go from 4x equals 12 to x equals 3? If you were solving this on your own, how would you have gotten to that final answer? Hopefully, you would have divided both sides of the equation by 4. So, what property, definition, postulate, theorem says that it's okay to divide an equation by the same number as long as that number isn't 0? The division property of equality. And there you go. Your first proof is done. That wasn't so hard, was it? Let's try another one. So when faced with a proof for the first time, what is the first thing we should do? Get our free points. With that out of the way, let's work through the problem. First, most students like to get rid of the fraction. I don't know why people hate fractions so much. So many haters. But if we did get rid of the fraction, we would end up with this. What did you have to do to get rid of that fraction? You had to multiply both sides by 3. What says that you are allowed to multiply both sides by 3? The multiplication property. I didn't use the full formal name here. Some teachers won't allow that, but I'm fine with it. And now we come to a crossroads. There are 2 major ways to go from here, but which way is right? Is there only one right way? Do you think both ways would be okay? The answer is both are fine. Like many things in math, there are multiple ways to approach a problem. You are free to make the choice that makes the most sense to you. You can use whichever statements or steps that you want to make your way to the proof as long as you can justify your step with a valid reason. Some students will take quite the scenic route to get to the end, but as long as they justify the process correctly, it will be an okay way to go. This is possible solution number 1. Of the 2 ways, it is the more popular path students tend to take. Most students will distribute here. If we do that, we end up with 5x minus 5 equals 30. The reason we are allowed to do that is the distributive property. Most students will add 5 to both sides, so that's what I will do. The result of that is 5x equals 35. The reason I can add 5 to both sides of an equation is the addition property. We finally get to the proof, but how did I get from 5x equals 35 to x equals 7? I divided both sides by 5. What says I'm allowed to do that? The division property, and we are done. However, I said this was just one possibility. Let's quickly look at the other possibility. Here we are back at this step again. You'll notice I have chopped off one line. This possible solution takes one less step. Despite that, it is still the less popular way for students to go. But let's just quickly show that this is a perfectly valid way to go also. The other way to go from this step is to divide by 5. If we do that, we end up with x minus 1 equals 6. The reason that is allowed is the division property, and we are to our final step. How did we get here? We added 1 to both sides of the equation. What says I'm allowed to do that? The addition property. So this just illustrates that you can go about proofs in multiple ways. As long as you justify everything correctly in the reasons column, you can take whichever path you like. Now let's look at a geometric proof. Here we have a simple one, even though that may not look simple to you at the moment. Like most geometric proofs, there is a picture included. Your first step is still the same. Free points! You'll notice that even though the picture is given information, you do not have to redraw the picture in your first statement. I have given you the statements. For a little bit here, we will give you the statements on geometric proof. Consider it your training wheels. At this stage, it would be cruel and unusual punishment to make you come up with them on your own. So let's go through how we justify each step. Generally speaking, the next line in a proof usually comes from one of 2 places, either the picture at the top or the statements that came before it. For statement number 2, it comes from the line above it. Look at statement number 1 compared to statement number 2. They are very similar. What's the only difference? If you look, AG has been added to both sides of the equation. Why are we allowed to add the same thing to both sides of the equation? The addition property of equality. It works the same here as it did in the algebraic proofs. Now let's look at the statement number 3. You'll notice that this line actually has 2 statements on the same line separated by a semicolon, and that's okay. You are allowed to have two statements on the same line if they both use the same reason. And guess what? These two use the same reason. These two statements come from the picture. If you look at this equation, it says that we're taking this segment and adding it together to make the really big segment. Similarly, for the other side, we are taking AG and adding it to GE, and that makes this big segment. In Chapter 1, there was a postulate that said we were allowed to take two pieces like that and add them together to form a bigger piece. The segment addition postulate. You need to remember that name. It will come up a fair bit. And finally, the last step. This is the hardest one for students to often see. Statement number 4 comes out of both statement number 2 and statement number 3. You should notice that SA plus AG appears on both lines. Similarly, AG plus GE shows up in both lines. How is that helpful? Well, in statement 3 we say that SA plus AG is equal to SG. If we look at this second line, we have SA plus AG, and what we're going to do is we're going to substitute the SG in for that piece. So I'm going to put SG here. I'm allowed to do that because I know that SG is equal to SA plus AG. Over here I have AG plus GE, and over here I have AG plus GE. Statement number 3 tells me that AG plus GE equals AE. So in this line I'm going to replace this with the thing that it's equal to, namely AE. By doing this, my equation over here has changed to SG is equal to AE, which happens to be what I'm trying to prove. So that's the process. It's hard for students to initially see, and dear Lord, look how many red lines I've got running through my page now. But I gave you a hint even earlier. I even said the word as the reason for what we use on this line. It's the substitution property. I substituted. I replaced this with the thing it was equivalent with. That's substitution. I told you that substitution shows up a lot in geometric proofs. It shows up a surprising amount. If you are doing a proof and have absolutely no clue for the reason on a step, throwing in substitution property will be correct a shocking amount of the time. So there is your introduction to geometric proof. Don't worry if it seems a bit overwhelming at the moment. You will be doing a lot of practice with them, and over time you'll get used to it. And heck, soon you'll be coming up with your own statements too, and not break a sweat over it.